Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we covered trigonometry. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with right triangle trigonometry. The six trigonometric ratios. The right triangle is the historical entry point to trigonometry, and it remains the cleanest place to learn the six basic functions. Take any right triangle and pick one of its two acute angles. Call it theta. Three sides of the triangle now have specific roles relative to theta. Figure 12. A right triangle with one acute angle labeled theta. The hypotenuse h runs from the right angle to the far vertex. The leg opposite theta is labeled O. The leg adjacent to theta is labeled A. The three labels rotate if you switch to the other acute angle. What is opposite for one angle is adjacent for the other. The six trigonometric ratios of theta are built from these three sides taken two at a time. Three are primary: sine, cosine, and tangent. Equation 3, the three primary ratios. Sine of theta equals opposite over hypotenuse. Cosine of theta equals adjacent over hypotenuse. Tangent of theta equals opposite over adjacent. Here O is the opposite leg, A is the adjacent leg, and H is the hypotenuse. The other three ratios are the reciprocals of these: cosecant, secant, and cotangent. Equation 4, the three reciprocal ratios. Cosecant of theta equals hypotenuse over opposite. Secant of theta equals hypotenuse over adjacent. Cotangent of theta equals adjacent over opposite. Each one is the reciprocal of the corresponding primary ratio. The mnemonic SOH-CAH-TOA captures the three primary ratios in order. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Figure 13. The SOH-CAH-TOA mnemonic decoded. S for sine equals opposite over hypotenuse. C for cosine equals adjacent over hypotenuse. And T for tangent equals opposite over adjacent. Memorize this one group and all three primary ratios are locked in. The reciprocal ratios are the upside-down versions. Worked example: finding a height. You stand 30 meters from the base of a tree on level ground. You measure the angle of elevation to the top of the tree as 42 degrees. How tall is the tree? Figure 14. The tree height scenario. An observer on level ground 30 meters from a vertical tree sights its top at an angle of elevation of 42 degrees. The 30-meter horizontal distance is the side adjacent to the 42-degree angle, and the tree's height is the side opposite. The ratio of opposite to adjacent is the tangent, so the tangent of 42 degrees equals the height divided by 30. Tangent of 42 degrees equals height over 30 meters. Multiply both sides by 30 to isolate the height. Height equals 30 meters times the tangent of 42 degrees. A calculator gives the tangent of 42 degrees as approximately 0.9004, so the height is approximately 30 times 0.9004. Height is approximately 30 times 0.9004, which gives approximately 27.0 meters. The tree is approximately 27 meters tall, measured without ever climbing it. Worked example: finding an angle. A ramp rises 1.2 meters over a horizontal distance of 8 meters. What angle does the ramp make with the ground? Figure 15. The ramp scenario. An inclined surface rises 1.2 meters vertically over a horizontal run of 8 meters, meeting the ground at unknown angle theta. The rise is opposite the angle of inclination theta. The horizontal run is adjacent. So the tangent of theta equals 1.2 over 8, which equals 0.15. Tangent of theta equals 1.2 over 8 equals 0.15. To recover the angle from the ratio, apply the inverse tangent, the arctangent function. Theta equals the arctangent of 0.15, which is approximately 8.53 degrees. The ramp is inclined at approximately 8.5 degrees. Try it. The leaning ladder. A 6-meter ladder leans against a vertical wall. The base of the ladder is 1.5 meters from the wall. Part A. What angle does the ladder make with the ground? Part B. How high up the wall does the top of the ladder reach? Pause the video now and give it a try. Here's a second problem. Try it. The cliff and the sailboat. From the top of a 50-meter cliff overlooking the ocean, you spot a sailboat at an angle of depression of 7 degrees. The angle of depression is measured downward from horizontal. How far is the boat from the base of the cliff? Pause the video now and give it a try. Why the ratios depend only on the angle? A subtle but essential fact makes the whole subject work. The values of sine theta, cosine theta, and tangent theta depend only on the angle theta, not on the size of the triangle. A right triangle with a 30-degree angle gives sine of 30 degrees equals 0.5, whether the hypotenuse is 1 centimeter or 1 kilometer. This is not an accident. It follows directly from a single result in geometry. The geometric fact is similarity of triangles. Two triangles are similar if their corresponding angles are equal, and when triangles are similar, their corresponding sides are proportional. Now consider two right triangles that share the same acute angle theta. Both have a right angle and both have theta, so their third angles must also be equal. The two triangles are therefore similar. The ratio of any two specified sides is therefore the same in both triangles, regardless of size. Animation 3. A right triangle with acute angle theta is drawn. A numerical readout below displays the value of O over H, the sine of theta. The triangle grows and shrinks while theta stays fixed. Both legs and the hypotenuse change with the scale, yet the ratio O over H never changes. It stays pinned to the same decimal at every size. Sine, cosine, and tangent are scale-free. They depend on the shape of the triangle, never its size. Figure 16. Two right triangles share the same acute angle theta, but differ in size. The small one has legs 3 and 4 with hypotenuse 5. The large one has legs 6 and 8 with hypotenuse 10. The ratio of opposite to hypotenuse is 4/5 in the small triangle and 8/10 in the large one. Both equal 0.8. This is why we can talk about the sine of 30 degrees without specifying which triangle we are looking at. Every right triangle with a 30-degree angle has the same set of ratios, so sine, cosine, and tangent are well-defined functions of the angle alone. Many functions you have met have inputs and outputs in different units. For example, the volume formula V equals PIR squared H takes lengths in meters and returns volume in cubic meters. Sine, cosine, and tangent take an angle as input and return a pure number with no units. Why is that? What does it tell you about what these functions actually represent? The special triangles and exact values. Most angles do not have nice exact sine and cosine values. but two triangles drawn from elementary geometry give exact values for 30, 45, and 60 degrees, values you will use again and again. These are the special triangles. The first is the 45-45-90 triangle, obtained by drawing a diagonal across a unit square. Animation 4. A unit square appears on the canvas, all four sides labeled 1, all four corners marked with right-angle squares. A diagonal is drawn from corner to corner, splitting the square into two congruent right triangles. One triangle separates out, two legs of length 1, and the Pythagorean theorem gives the hypotenuse as the square root of 2. The two acute angles are equal and must sum to 90 degrees, so each is exactly 45 degrees. From this triangle, the exact trigonometric values of 45 degrees follow directly. Equation 5. The 45-degree exact values, sine of 45 degrees and cosine of 45 degrees, are both equal to 1 over the square root of 2, which equals the square root of 2 over 2. Tangent of 45 degrees equals 1. Opposite and adjacent are the same length in this triangle. The second is the 30-60-90 triangle, obtained by cutting an equilateral triangle in half along its altitude. Animation 5. An equilateral triangle of side 2 is drawn. All three sides labeled 2, all three angles marked 60 degrees. An altitude drops from the top vertex to the midpoint of the base, cutting the triangle exactly in half. One half separates out. Hypotenuse 2, short leg 1, half the base, and long leg equal to the square root of 3 by the Pythagorean theorem. The acute angles are 30 degrees at the top, half of the original 60-degree vertex, and 60 degrees at the base. Reading the ratios off this triangle gives the exact values of sine, cosine, and tangent at 30 and 60 degrees. Equation 6. The 30-degree exact values. Sine of 30 degrees equals 1/2. Cosine of 30 degrees equals the square root of 3 over 2. Tangent of 30 degrees equals the square root of 3 over 3. Equation 7. The 60-degree exact values. Sine of 60 degrees equals the square root of 3 over 2. Cosine of 60 degrees equals 1/2. Tangent of 60 degrees equals the square root of 3. Notice that sine and cosine swap between 30 and 60, a hint of the cofunction relationship to come. Figure 17. The two special right triangles side by side. On the left, the 45-45-90 triangle with legs 1 and hypotenuse square root of 2. On the right, the 30-60-90 triangle with hypotenuse 2, short leg 1, and long leg square root of 3. Every exact trigonometric value at 30, 45, or 60 degrees can be read directly from one of these two triangles. A pattern worth noticing: the sine values for 0, 30, 45, 60, and 90 degrees can be written as square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, and square root of 4 over 2. Figure 18. The square root pattern. Sine values at 0, 30, 45, 60, and 90 degrees are the square roots of 0, 1, 2, 3, and 4, each divided by 2. The cosine values are the same list in reverse. Cosine of 0 degrees equals 1, and cosine of 90 degrees equals 0. Worked example, exact area. An isosceles triangle has two sides of length 6 centimeters with a 30-degree angle between them. Find its exact area. The area of a triangle equals 1/2 the product of two sides times the sine of the included angle. Substitute the two side lengths of 6 centimeters and the included angle of 30 degrees. Area equals 1/2 times 6 times 6 times sine of 30 degrees. Use the exact value. Sine of 30 degrees equals 1/2. Area equals 1/2 times 6 times 6 times 1/2, which is 18 times 1/2, which equals 9 square centimeters. The area is exactly 9 square centimeters. No decimal approximation needed. Try it. Exact values. Without a calculator, compute the exact values of Part A, sine of 60 degrees plus cosine of 30 degrees. Part B, tangent of 45 degrees minus sine of 30 degrees. And Part C, sine squared of 60 degrees plus cosine squared of 60 degrees. Use the special triangle values, not decimal approximations. Pause the video now and give it a try. Reciprocal and quotient identities. From the definitions of the 6 ratios, a few small identities follow at once. They are useful enough that you should know them by sight. The reciprocal identities simply restate the definitions of cosecant, secant, and cotangent. Equation 8. The reciprocal identities. Cosecant of theta equals 1 over sine of theta. Secant of theta equals 1 over cosine of theta. Cotangent of theta equals 1 over tangent of theta. The quotient identities express tangent and cotangent in terms of sine and cosine. Equation 9. The quotient identities. Tangent of theta equals sine of theta over cosine of theta. Cotangent of theta equals cosine of theta over sine of theta. These follow directly from the ratio definitions. In a right triangle, dividing O over H by A over H gives O over A, which is exactly tangent theta. So tangent of theta equals sine theta over cosine theta is not a new fact about trigonometry. It is a fact about how 3 ratios sharing a common denominator simplify. Try it. Verify the identities at 60 degrees. Compute all 6 trigonometric values for theta equals 60 degrees, using the exact special triangle values. Verify that cosecant of 60 degrees equals 1 over sine of 60 degrees, secant of 60 degrees equals 1 over cosine of 60 degrees, and cotangent of 60 degrees equals 1 over tangent of 60 degrees. Then verify that tangent of 60 degrees equals sine of 60 degrees over cosine of 60 degrees. Pause the video now and give it a try. That wraps up right triangle trigonometry. Next up, Section 4, the unit circle, trigonometry for any angle. If you found this helpful, like and subscribe and support the channel.